So you can explain in some theories these signals that have been observed. So far we've had a few contradictory results. Maybe they're indicating that we're getting close to the needed sensitivity. Maybe they're just experimental issues, but it's a very exciting point in time because we do have a few interesting signals. Now let me tell you a couple of words about indirect detection. That is, like I said, what I mostly work on. So the picture here is that our Milky Way is embedded in this big halo of dark matter, and within this halo, particles making up the dark matter can annihilate and produce a bunch of particles that we can actually detect. Okay, and among these particles are antimatter. So the idea is to detect antimatter to study dark matter, which is kind of funny, but antimatter is sufficiently rare that you can use the detection of antimatter to constrain rare processes like the annihilation of dark matter. You've got gamma rays, and so you can use telescopes like Fermi, and I believe somebody has already told you about activities related to the Fermi Gamma Ray Telescope here in Santa Cruz. Fermi also detects positrons and electrons. Positrons, as you might know, are the antiparticles of electrons. And these guys also lose energy and produce radiation at other frequencies than gamma rays, for example, X-rays. So you can use telescopes like Chandra, which is an X-ray telescope, to study these positrons and electrons. They also produce radio emissions, so you can use synchrotron radiation to study them. And then there's high-energy neutrinos, and we've got a bunch of really cool telescopes that look for high-energy neutrinos. So all of these are different channels for what we call indirect dark matter detection, and there's many follow-ups. AMS, for example, is now operating on the International Space Station. It's got really cool results on antimatter. This is a proposed future array of ground-based gamma ray telescopes. This is a future X-ray telescope, and Planck is a new satellite that the Europeans have put on orbit to study radio emission. So the question that my research program addresses is whether or not we can actually study dark matter by using the information coming from all of these indirect channels. Okay, so can you use antimatter to learn anything about dark matter, gamma rays, and so on? And I think it's very interesting because, as you can see, it's a multi-messenger problem, so you have many different channels that you use to study this problem. And the other interesting thing is that there's a lot of astrophysics that goes into this, because astrophysical processes produce each one of these messengers. So spallation of cosmic rays produces antimatter, high-energy neutrinos are produced in many astrophysical processes, and so on. So it's interesting to understand and fight these astrophysical backgrounds, and of course, life is always kind of ironic, and the worst astrophysical backgrounds coincide with the most exciting places where you might look for a signal. So there's a few things that might point towards dark matter. We know that there's many more positrons in the galaxy than there should be, so maybe some of these positrons are produced by dark matter, and AMS has confirmed this extra amount of positrons. There's a feature in the galactic center that also might point to dark matter. So if you look at the center of the galaxy, there's more gamma ray emission than there should be, and that might be associated with dark matter annihilation. And my students and I have worked pretty hard to understand whether or not this is due to astrophysics or to dark matter. And then recently, we've had a lot of excitement because we've seen a line in the gamma ray data, and this line might be associated with the process of two dark matter particles going into two photons. Okay, and these two photons have an energy exactly equal to the mass of the dark matter particle. So if the line is in fact there, and there's no astrophysical process that could cause this line to exist, then we might have a discovery not only of a dark matter signal, but of the dark matter mass itself. And this line happens to be at 130 GeV, which is an interesting energy scale, close to the Higgs mass, so telling us maybe dark matter has to do with the Higgs sector. So let me tell you a little bit about other activities in particle physics here at UCSC. So you've got me. I work on dark matter and other aspects of cosmology. You've got Howie Haber, Michael Dine, who's also department head, and Tom Banks. So I'm going to tell you a little bit about my three colleagues. So Howie is also known as the Higgs hunter. He played a huge role in understanding the theory behind the Higgs boson. And one of his books is The Higgs Hunter's Guide. And this was the fundamental textbook for folks looking for the Higgs at the LHC. And of course, the Higgs discovery made a huge impact also on popular news. So The Economist had a whole cover on the Higgs boson. And as you can see, this guy is sleeping in front of a supernova explosion. So maybe suggesting that the Higgs has something to do with cosmology. That might or might not be true. Michael Dine is known for the axion. Here's a picture of the axion. Well, the axion is a particle, but there used to be a cleaning product called the axion, so we always make fun of this. And he's also very well known for baryogenesis, which is a theory behind the matter-antimatter asymmetry, and I've also been working on that quite a bit. And then Tom Banks is very well known for string theory and also for early contributions to the theory of strong interactions. And here's a summary of string theory. This guy says, I just had an awesome idea. Suppose all matter and energy is made of teeny vibrating strings. Okay, what would that imply? And he says, I don't know. String theory has this issue of not making any testable real predictions, but we do think that string theory is kind of the way to put gravity and the other interactions in the same place, and Tom is one of the key players in this. And so I think this is actually everything I wanted to tell you. So the cosmic puzzle is definitely far from being solved, but we at least can name names. We at least know that the big missing pieces are dark matter and dark energy, and we have well-motivated candidates for both, but we don't have any direct evidence for any of these candidates. And so I think it's a very, very interesting place to be as a scientist. And yeah, and Santa Cruz has been making huge contributions to this field. So if you're interested or have any follow-up questions, I'd be more than happy to hear from you. Thank you very much for your attention.
I was wondering how kind of more obscure theories like the holographic principle may fit into some of this more standard and logical science going on.
Well, the holographic principle is actually something that Tom, my colleague, kind of fathered.
Really?
Yeah, absolutely. So he's very actively working on it. And I mean, the general issue to me is that holography doesn't really make any testable prediction. So there's a famous philosopher of science, Karl Popper, that says that you can call science something that you can falsify, something that you can build an experiment, and if the experiment has a certain outcome, the theory dies. And holography, as well as other aspects of string theory, don't have that. So is it science? I think it is, because from a theory standpoint, from a principle standpoint, you know, you have very sound mathematical foundations, and you're pursuing a very noble goal, which is to unify gravity with our interactions. But there is this big question of, can we make testable predictions? And so far, holography hasn't really made any of these predictions, but I mean, it is a mathematically very sound framework. So,
isn't there an experiment going on out of Chicago right now that's supposed to test the static jitter of this holographic two-dimensional space?
I don't know about this experiment, but
It's looking at, so it's
Okay.
bouncing a laser beam. It's like the same type of experiment looking for gravitational waves,
okay.
but instead of gravity warping the space and affecting the travel time of the laser, it's going to be this static of the little finite-sized bits
Okay.
controlling three-dimensional space. So you'll have two of these set up. So if you see the same discrepancy in each one, then you know it's some underlying, like, fundamental feature of space that caused it to...
Yeah, you know, folks have thought about tests like that, and I don't know any detail about the experiment you're mentioning, but you know, there's things like there's other quantum gravity theories, like loop quantum gravity, that also would predict, you know, local features of space-time, you know, exhibiting quantum behavior. So, you know, you can hope to see something like that